Today's video will be about concentrations of solutions. What does that mean? Well, we know that in chemistry, when we have a solute and a solvent, or when we're mixing a few things together, at some point we need to figure out how much is there of one compared to the other. And that's what we're going to do today. So let's see if we can look at some definitions to start with. The first definition I have is about concentration. Now, in the last couple videos, I've talked about solutions, and I'm going to put a link here or here with my previous videos on solutions. But let's see. First of all, a concentration is the ratio of solute versus solvent. So that's the key aspect of what concentration is. But it can also be the ratio of solute with the overall quantity of a solution at the end. So here it applies to gases, liquids, and solids when they are mixed together. Keeping in mind that the solute is the quantity that is the smallest, and the solvent is the largest volume or mass, that the one that takes the most place in that solution. So let's see if we can add more to that. As I'm looking into my textbook, I realize that the next couple words that we need to look into are, what does it mean if you have a solution that is concentrated compared to if you want to dilute something? So let's see if we can take an example of orange juice. We have, let's see, do I have orange color? If we have an orange right here, what happens is we can take this orange and we can squeeze the juice out of it to get the orange juice. So this is orange juice that is freshly pressed. This is easy. It is not concentrated. The juice is not diluted. On the other hand, sometimes when you have too many oranges at the end of the season, what do? They take the orange juice and then they create what we call concentrated orange juice. So we go here, you see something like this, orange. Concentrated orange juice is what? We have the original juice and most of the time we evaporate it so that we have a smaller volume of the same juice. So what happens? We have here some orange juice, but it is concentrated. Concentrated like this. Perfect. Now, often we buy this at the grocery store. It is in the frozen section. Now we get home. What do? We have frozen juice, and now we want to have a juice that is closer to the original concentration of orange juice. So what do? We will dilute the concentrated orange juice into another container where we have an orange juice again, like this. And let's see if I can get the orange. And here we have orange juice from concentrated juice. And there we go. So this is a process here trying to explain to you when we have, for example, the fruit, we press the juice, we will evaporate the juice to let the water go, to have a higher concentration of the sugar, the citric acid, and all the good things in the orange. And then when we are ready, we will dilute this concentrated juice with water, and then we get the juice from concentrated juice. If you wanted to know, you can always check in the grocery store. You will see. You'll have fresh juice. You'll have juice from concentrated. Sometimes you even have a mix. So this is the basis for this. So this is the basis for this video today. If you've enjoyed what you've noticed, if you've enjoyed what you've learned so far, don't hesitate to subscribe to our channel. I'm working on building videos on different scientific topics so I can help you, either students, teachers, even parents, wanting to learn more about subjects that can get them to the next level in understanding our world. So my name is Alain Faber. I've been teaching for more than 25 years, and I'm making videos because I like to share what I know. These videos at this time I make for a person that I tutor. I haven't done this chemistry for a while, but guess what? I'm enjoying learning them again. So on this, stay with us. We're going to continue learning about concentrations of solutions. From this point on, I'm going to talk about 3 ways to understand percent concentration. And there's a few more things afterward, but let's focus on the first 3. Percent concentration can be defined as a mass volume percent, and often we call them as percent M over V. You can also have mass percent, which is mass percent, and you also have a volume percent. And here is percent V over V. We're going to describe what they are. We will also give an example for each of them. So let's start with the first one, mass volume percent. In this first example, let's see if we can look at the equation that will help us. You will notice that most of the equations are very similar one to the other, and let's see if we can have a better understanding. So here the percent mass over volume, and we can call them also mass volume percent, is equal to what? It's the mass of the solute in gram over the volume of the solution. So the final volume of what you have at the end times 100. So here I have an activities that was in the textbook. It goes like this. You've got a pharmacist, and the pharmacist adds 20 ml of distilled water, and it adds that to 30 grams of medicine. So the question here, we're looking for the percent concentration, or because we have a mass and here there's a volume, we have mass volume percent. Now there's an extra sample or extra information that is given here. So let's see. We have that the final solution, the volume of the final solution is 25 milliliter. So here it's important. So we're not talking about the fact that 20 milliliters of water were used. We're looking for the volume of the solution at the end. So we're not going to use the 20 ml. We're going to use here the total volume of the solution at the end. So that's something to keep in mind, because when we have a solid takes room, and there's a volume to that, and it can affect the equation. So let's see if I can put the information here for this problem. If I'm looking for the percent, here the percent concentration, we have the mass of the solute, which is 30 grams, divided by the volume of the solution, and we have here 25 milliliter. And if we are to do the calculations, I did that on my booklet. I have here, oops, I forgot. We're looking for percentage times 100. We end up with 30 divided by 25. That gives us 1.2 times 100. We have 100% 120% concentration based on the percent mass volume, like this. So here's an example of the calculation. Now we're going to do another one, because what happens if instead of having the mass of the solute and the volume of solution, if you start with what you're looking for and you're looking for the missing information. Let's see if I can give you another example in one moment. So let's see if we can figure out this information here. We have a problem that goes like this. If we were looking for the mass of potassium permanganate that we will need to mix into a final volume of solution of 2 liters, and then from there we want to have a solution of 4% mass over volume solutions. Now you have to keep in mind, in here the solution we're looking into milliliters. So let's see. We just have to plug in the numbers. We have here the percent concentration, which is 4%, equals the mass in gram of the potassium permanganate. We don't know that information yet. Over the volume of the solution, we have 2 liters, therefore we have 20 milliliters times 100%. Now what we have to do, we need to isolate the mass of potassium permanganate that we're looking for. So here, Because I am divided by 2000, I will multiply on the other side of the equal sign. And here we have multiplying by 100. We will divide by 100 on the other side to isolate the mass. So what do we have here? The percent here change. We have milliliter here and here. So the units are being canceled. We end up with G like this in gram. So we have here 400 divided by 100 times 2000. So let's see if we can do it without a calculator. We have divided by 100. Here we have 20 left. 20 times 4 is 80. So we have 80 grams, which is the mass of potassium permanganate. So I was looking, so it seems that we can give 80 grams is great. Some people like to use sometimes the scientific notation. So here, if I want a number between 1 and 9, we can do 8 times 10 to the power of 1 gram. And that will give us the exact same answer. So hopefully this helps you understanding this one. In a moment, we will look at how can we calculate the percent concentration of mass percent. So that's the next question that is coming along. So now we're going to look at a second way to look at percent concentration, and it is mass percent. That means a ratio between two masses. I'm going to start to stay excited because this is the second time the third time I record this segment, and guess what? I keep forgetting to press record. So let's see if I can answer the question, and that's why we have all the information here. But let's see if we can, first of all, understand the equation. If you're looking for a mass percent, we're looking for the ratio between two masses. And here it is the mass of solute over the mass of the solution you are working with. And then keeping in mind that often you have the solute will be a smaller portion of a bigger mass times 100%. Very similar to previous example we've done so far about percent concentration. Now, interestingly enough, here this works wonderfully when you have what we call solid solution. So an example for that will be if you take this bottle in stainless steel. In order to make this, you need several metals put together. But how do you measure them? The best thing is if you know the ratios of different metals to make stainless steel, then you can measure the mass of all the different metals you need, put them together, melt them, and get what you want. And that's exactly the example I'm going to show you in a moment. Perfect. So here is the example. It's number 13 in my textbook. And the idea here is we have a company wanting to create an alloy, which is stainless steel 18-8. This is a type of stainless steel. The 18-8 means that there's 18% chromium and 8% nickel. Now, on top of this, if we assume that the third metal, that's the only one that they add, is iron, that means that we have 70% that would be of the mass, that would be iron. Now, it's possible that there are other types of metals. I'm just simplifying it here, but in metallurgy, I'm sure people are inventing new ways to create alloys. Now, on top of this, they're saying that we want to create a batch that is weighing 500 kilograms. That means that if you have 500 kilograms of an alloy, within that 500 kilograms, you have a certain amount of kilograms for each of the metals involved. And here, 18% of that 500 kilograms would be chromium, 8% of the 500 kilograms would be nickel, and 74% of the 500 kilograms would be iron. So here, this equation works wonderfully. So if I'm looking for the mass of solute, let's say that I'm looking for how much chromium is within this stainless steel, I need to isolate the mass of solute. Keeping in mind that in a word problem, we have 3 unknown. If you keep algebra fairly simple, if you have 3 unknown and you can give me 2, I can isolate the variable I need to figure out the answer. So here, if I'm looking for the mass of solute, here, I will isolate this one. That means I have percent mass over mass. I multiply by 100 on this side, I will divide on the other side. And since I'm dividing by the mass of the solution, I will multiply on the other side of the equal sign giving me this equation here. The mass of the solute is the percent mass. So mass over mass divided by 100% times the mass of the solution. So I've done all the calculations like this because I told you I thought I was recording, but let's see what my gibberish here looks like, and you'll see it's quite simple. If I'm looking for the mass of chromium, we know that it's 18% of the whole batch. That means that the mass of chromium is 18% divided by 100 times the mass of the overall solution. And this is a batch of 500 kilograms of stainless steel. So here, if you think of a solution, we don't talk about a solution that is a liquid, but a solution that is a solid. So we call them solid solutions. Here we simplify here, we cancel out the percentage, we can cancel out the hundreds. So therefore 18 times 5 gives us 90 kilograms of chromium. That means that the mass of chromium in 500 kilograms of stainless steel would be 90 kilograms. Perfect. So that's the first piece of information. I want the same thing for nickel. So the mass of nickel is the mass percentage of nickel, 8% divided by 100 times 500. We do the simplification of the percentage to hundreds. 8 times 5 gives us 40 kilograms of nickel. So here I have the second component. Now the last one is iron. I can do the same calculations here. We have the mass of iron, which is the percent mass, the mass percent, which is 74% divided by 100 times 500 kilograms. The percents here cancel out, the hundreds as well. 74 times 5 gives us 370 kilograms of iron. So that means that if I had 500 kilograms of stainless steel, 18.8, I will need to create that 90 kilograms of chromium, 40 kilograms of nickel, as well as 370 kilograms of iron. And that's how the mass percent is working when you are comparing the ratios of two masses. So hopefully you've learned something fun, and keep in mind that in a moment we'll talk about volume percent, and then at the end of the video I'm going to give you a fourth way to measure concentration of solutions, and you'll see I love this one, and I'm sure you'll be interested. I'll see you in the next segment. Now let's look at our third percent concentration that we have on this list, and it's called volume percent and V over V. What does that mean? Remember that we've done two already, mass over volume percent, and we have mass percent. Here, what we have is another equation, and you'll see they're all very similar. The volume percent, V over V, it's good for liquids. We have the volume of solute over the volume of solution times 100%. So here, keeping in mind that for the first one we had here, we had, for example, a certain mass of a solid that we wanted to dissolve in a volume of liquid. For this one here, we had the idea that if we have solid solution, we have several metals, several solids we want to put together. Masses work well. And then we have volume percent with two different volumes. So I have a word problem for us to see how we can work it out. This is number 23 in the textbook, and let's see. We have a company who wants to create a windshield fluid to clean the windows. We know that in the problem that we want to create a 4-liter container of windshield fluid. And the company wants to have 40% of methanol in that product here. And we're looking for what is the quantity of methanol do I need to have a 40% methanol in 4-liter container. So given this information and what we have here, let's see if we can figure it out. So here we are looking, let's see if I can get let's get the red one. We have here the volume of solution. That is great. We also have the volume percent, which is 40%. The only thing missing is the volume of solute. And it works well because methanol is a smaller volume compared, it's 40% instead of the 60% of water that is added. So here we can find the missing information, which is volume of solute. So let's see if I can isolate this variable, and we'll do the calculations together in one moment. So let's see if we can find how much methanol we need to create that windshield fluid. We know that the volume of solute in methanol will be equal to the volume percent of the solution divided by 100, because we have the volume percent equal, if we multiply by 100 on one side, we will divide in the other. And here we are dividing by volume of the solution, and therefore on the other side of the equal sign, it will be a multiplication. So we have the volume of methanol equals the volume percent over 100 times the volume of solution we have. We know that the volume percent is 40%. We also know that the volumes of the solution is 4 liters of windshield fluid, and that's what we want to create at the end. So let's see if we can do the calculation. Let's get another color. So the percentage are canceling out. So here we have 40 times 4, which is 160 divided by 100. That will give me 1.6 liter of methanol. Like this. So this is what we need. We need 1.6 liter of methanol and to create a 4 liter of windshield fluid. Now we have to be careful because we don't need 1.6 liter of methanol and then 4 liter of water, because the total volume is actually 4. So if the total volume of the windshield fluid, total volume of the windshield fluid, if it is 4 liter, that means that if we have 1.6 liter of methanol, we will need 2.4 liter of water like this. And it's important because when you add the two together, then you get the overall volume of the solution. So to create a 4 liter volume of windshield fluid, you need 1.6 liter of methanol and you need 2.4 liters of water. So here, this is an equation with 3 unknowns. In all the word problems you're going to have to do, they will give you 2 pieces of information and 1 unknown. You just have to plug in the numbers, and then find the answers. On this, hopefully you have appreciated these 3% concentration we've seen so far. And guess what? In a moment, I'm going to give you an extra one, and you'll see that one is exciting. So here is a 4th way to look at concentration of solutions. So let's see, it's called molar concentration. Now, depending on the books you are working with, people call it molar concentrations, or it could also be molarity. When I went to school, we called it molarity. It was one word, it was easy. In the textbook, I noticed it's called molar concentration. It's the same thing. So here, when you have a concentration, it is also a ratio. Interestingly enough, so far we've talked about the percent concentration, and here we have the ratio between mass and volume. Here we had the ratio of mass over mass, and here the ratio of volume over volume. So for this one, the 4th one, it's a bit different because we're looking for a molar concentration, and here, and when I say it, you'll see it's based on something we've learned before. The molar concentration will be the amount of solute here in mole over the volume of solution in liter here. So here it is the basic equation for it. So I'm going to share with you an example. So molar concentration is something great because when I work with acids and base, I love the idea that I can create my solution for my lab. So here, the example I have is that I have sodium hydroxide, and I want to create a solution of 1.0 mole per liter. If you've done grade 10, science, if you've done other science lab, you have seen mole per liter in the past. So you'll understand at the end what it's from. So if I'm looking for 1.0 mole per liter of sodium hydroxide, what I need to do, I need to take my equation and I need to say, okay, the molar, so I want 1 mole of sodium hydroxide per 1 liter of water equals the amount of NaOH in mole over 1 liter of water. So here, if I want to know my unknown, I will isolate it. So here, let's see if I can change color, may as well. So we have the amount of NaOH in mole like this equals 1 mole of NaOH per liter of water. I need a bigger board here. Over, so let's see. I want to isolate this, so we have this as a numerator times. So let's see if I can rewrite this to make sure it works. So we have 1 mole of NaOH over 1 liter of water, or per liter of water. And here, because I divide by 1 liter of water, I will multiply on the other side. 1 liter of water. Like this. So here we can do some simplification. We can simplify those two here. So here the amount of NaOH I need is 1 mole. That's easy because we're all working with ones. If I was looking for 2 moles per liter or 6 moles per liter, I'd have a similar example. But the big question here is how much of NaOH do I need? I need to have 1 mole of NaOH. So how do we calculate this quantity? And this, we need to go back to what we've done in the past. And I'll see if I can put a link here to a previous video on molar mass. But here, to find the molar mass of sodium hydroxide, I need to look at the molar mass of each of the atoms in the molecule. I will add the molar mass, and I have here a nice round number, and I have 40 grams. The 40 gram here is the molar mass of sodium hydroxide. Therefore, if I'm looking to create 1 mole per liter of sodium, if I'm looking for to create 1 mole of sodium hydroxide, I need to have 1 mole of here. Sodium hydroxide, there you go, and it is 40. So in order to have my molar concentration of 1.0, let's see if I can write it down, 1.0 mole per liter equals what? I need 40 grams of NaOH over 1 liter of water. And this is how we are working with molar concentration. We're not talking about mass, we're not talking about volumes, we are talking about mole, based on all the work we've done so far with stoichiometry and as well as looking at molar mass of molecules. So there you go. And so that's the 4th one. I think it's interesting, and I'm sure you would appreciate. On this, if you've enjoyed the video so far, don't forget that it's always good to subscribe to my channel. It supports me and it allows me, with your comments, to know what other videos you'd like me to do. So on this, put your comments in the video with the clarification questions you have or any other topics for future videos. And on this, I will put on this side another video for you to go and watch. And I'm also going to put a playlist of a variety of science video about chemistry that you might like. On this, I'll see you in the next video.